Good morning to all of you. In this lecture, I am going to discuss the another application of Gauss law, which is the line charge density. Means we have to find out the electric field due to a infinitely line charge having line charge density lambda. So this is another application. So using Gauss law, we can find out the electric field due to a infinite line charge having line charge density lambda. So we have already discussed that symmetry play a very crucial role to apply the Gauss law. So if we have a point, so we can draw for a spherical symmetry. There are three important symmetry in Gauss law, that is spherical symmetry, cylindrical symmetry and planar symmetry. So corresponding to these three symmetry, we have three different kinds of Gaussian surface. If we have a spherical symmetry, the corresponding Gaussian surface is Gaussian sphere. If we have a cylindrical symmetry, so corresponding Gaussian surface is coaxial cylinder. If we have a planar symmetry, so we have a corresponding Gaussian surface is the Gaussian pillbox. So in this case, we have an infinite line charge. So corresponding this is simply a cylindrical symmetry. So in order to find out the electric field, we have to draw the coaxial cylinder, or we have to draw a cylinder in order to analyze this problem. So we have an infinite line charge. We have infinite line charge having charge density which is lambda. So charge density is simply dq by dl, or dimensionally q by l. So let us draw a cylinder. So in order to find out the electric field, draw a Gaussian. What is our first step in Gauss law? Identify the geometry or recognize the geometry, draw the corresponding Gaussian surface. So this is wire. So corresponding Gaussian surface is cylinder. So that is why we have to draw a Gaussian surface. Sorry. Of length L. So this is the, and we want to find out the electric field. So applying Gauss law, which is Gauss law states that flux through any closed surface, which is E dot ds, is equal to charge enclosed in that surface divided by, so we have a charge q and line charge density. So what we have information about line charge density lambda, because this is infinitely extended wire. So corresponding Gaussian surface is cylindrical. So Gaussian surface is and Gaussian geometry is cylindrical. So we can find out, in this case this is bit more different from the earlier case. In earlier case, we have discussed the concept of Gaussian sphere and spherical cell, means uniformly charged solid sphere and spherical cell. In this case, we have a infinitely extended, the line charge density is of this wire is lambda, and length of this cylinder is, why we are drawing cylinder, because we have an infinitely extended wire, and the corresponding Gaussian surface, if we have a wire, so corresponding Gaussian surface is cylinder. That is why we are, and in this case, in cylinder we have, if this is cylinder C, so we have three different surfaces, surface 1, surface 2 and surface 3. And the radius is, this one is R, this one is R. So we can find out the electric field at any point. So this is, this is surface 1, this is surface 2, and this is surface C3. So we have three different surfaces. In sphere we have simply surface of a sphere, but in cylinder we have this one. This is one surface, and this is another surface, and that is another surface. So we have three different, in case of cylinder or in cylindrical geometry, we have three different surfaces. So what is, we have to find out the charge enclosed and flux through three different surfaces. So what is our Gauss law? Simply, this will simply E dot ds corresponding to surface 1 plus surface 2 E dot ds plus surface 3 E dot ds is equal to charge enclosed in that surface divided by free space permittivity. So anyhow we have to find out E dot ds corresponding to these three different surfaces. So before evaluating E dot ds, let us investigate what is E. In earlier case, E electric field is, earlier case means in case of uniformly charged solid sphere or spherical cell, the electric field is radially outward and area vector ds is already normal to the surface. So direction of E and ds are in same direction. So E dot ds is E ds cos 0. So we will simply evaluate the area vector or integral ds. But in this case we have different profile. If you consider a small area, so electric field, in this case electric field is radially outward. So from here to here, direction of electric field is radially, this is direction of electric field. And if you take the area vector in this surface, let me just roll this paper in order to visualize. So this is the situation that we have. This is the situation that we have, and we have this surface. We have we have this situation, that is surface 1, surface 2, and surface 3. In all these surfaces, electric field is radially outward. And what is area vector? In this case, if you take this surface, this side, so this side electric field is again this direction, and for this surface area vector is normal to this surface. So ds is in this direction. In this case, if you talk about this surface, so electric field is radially outward and the surface is this surface, so area vector is also normal to this surface. So ds is this one. And what about this surface? Electric field is radially outward and area vector is again ds. So in case of 1 and 3, E dot ds is, means area vector in this direction, E dot ds is E ds cos 90. Angle between, here theta is, angle between theta and ds is 90 degree. Here angle between theta and, angle between E and ds is, theta is 90 degree. And here theta is 0. Here theta, because electric field is radially outward, area vector is normal to this surface. But area vector in this case is in this direction, because this is separate, this is entirely different surface from this surface. Surface 3 and surface 1 is entirely different from surface 2. So that is why E dot ds is simply E dot ds, we know this is dot product E ds cos theta. So E dot ds corresponding to 1 and 3 is simply E ds cos 90, which is 0. But E dot ds corresponding to surface 2 is E ds cos 0 because they are in same direction. So this is the way to analyze the problem. So first we should find out the, or we will find out the E dot ds corresponding to three different surfaces, then find out the charge enclosed. But in this, for surface 1 and 3, E dot ds is 0. So this will cancel out and we have only surface 2. In this case, E dot, this is surface 2, which is E dot ds is q enclosed by epsilon 0. And ds is, what is ds in this case? In case of sphere, 4 pi r square. But for cylindrical, what is the area of cylinder? Circumference into length. Circumference into length. If what is the circumference? If r is the radius, then circumference of this cylinder is 2 pi r and length is l. So 2 pi rl is the area vector. So in this case, this is E into 2 pi r into l. And what is q? What is q? If lambda is the charge density of this infinitely extended wire, so from here q is, if lambda is the charge density, let me write, if lambda is the charge density, so charge, lambda is charge upon charge per unit length. So q is simply lambda l. Q is simply lambda l. This is one dimensional situation. So lambda l by epsilon 0. L will cancel out and we will have the final profile, which is lambda upon 2 pi epsilon 0 r cap. This is the electric field profile due to infinitely extended wire. Again, which is E is proportional to 1 by r. So this is the, you can plot this profile, plot the variation of E with r, and this is the way to analyze the. So in cylinder we have three different surfaces. For surface 1 and 3, we have E dot ds is 0. Flux through this 1 and 3 surfaces is 0. So we have only flux corresponding to this surface 2 because of the angle. So this is E dot ds, which is simply E into ds in this cylindrical area is 2 pi rl, E into 2 pi rl, and charge enclosed in this, if the line lambda is the line charge density of this wire, then total charge enclosed is lambda into length of the cylinder. So now putting the value and evaluating, we have lambda upon 2 pi epsilon naught r cap, and variation is E proportional to 1 by r. So it's all about the electric field due to infinitely line charge. Thank you.